This lecture, we are going to discuss a problem from TIFR examination, which actually resembles something called as time average potential of a hydrogen atom. So above problem was asked in TIFR 2017. This was asked in TIFR 2017, and you can see that this particular potential problem, all the answer have a Dirac delta function. Okay, so you can see how important has it become in as far as your examination part is concerned. So you can see that all these options contain some Dirac delta term. So obviously this particular potential will eventually lead to a charge density which would contain some Dirac delta function. So as we were discussing, we'll go along with this particular problem. So as you're aware that the above problem, you have only potential given. So del square phi is given by rho as a function of r divided by epsilon naught. Uh, this is your Laplacian equation. Okay, and in order to solve this Laplacian equation, what you do is you just use del square phi. This is your formula for Laplacian operator. This is 1 upon r square del by del r of r square and then del e r upon del r. So this is your del square phi. Okay. Now, in order to evaluate, sometimes it is called, I think, Poissonian equation, but overall, this contains Laplace, so that is why I have written it as a Laplacian equation. So overall, this represents your Gauss law, because you know that your del dot E vector from Gauss law is given by rho over epsilon naught, and you know that your electric field is nothing but it is equals to minus of grad of phi, because your electric field is a conservative vector field, so it can be represented as gradient of some potential, conservative potential. So therefore, I can write del dot E vector as del dot minus grad phi, and which would eventually give me del square phi is equals to minus rho over epsilon. So overall, you can understand that your what I can say, that your Gauss law can be written in the form of in this form also. Okay. Okay. So del square phi is equal to minus rho over epsilon naught. So if you can see that this is your Laplacian operator, and Laplacian operator when operated against a function of r, let's say here you have this not e of r, sorry, phi of r, it will give you 1 upon r square del by del r of r square del phi r upon del r. So this is typically the formula of your Laplacian acting upon a potential which is only a function of r. Okay. Now, as you're aware, I will do one slightly tricky kind of thing. So one tricky kind of approach I will take while doing this question, and one other standard approach I will also take. Let us say first thing how one can think about this in examination. As you're aware, as I've written that del square phi can be written as 1 upon r square, and then I have del by del r of, you have this r square, and then you have del phi over del r. Okay, so if this is the case, what I can do is, if I just use this particular formula, so first let me find what is my del phi upon del r. First, let us find what will be my del phi upon del r. It will be equals to del by del r of, and this will be, I think, q upon 4 pi epsilon naught. 4 pi epsilon naught, and then you have e to the power minus alpha r 1 upon r plus alpha by 2. So this is how it is. So if I use this thing, so I've just multiplied my 1 over r inside, and I can write in this fashion. Is that clear? Now, sorry, this is not del phi upon del r. This is my simply phi, and I have to differentiate it with respect to r. So I have to differentiate it with respect to r. So what will be my del phi upon del r? So del phi upon del r would be equals to q upon 4 pi epsilon naught comes out. Sorry, I've already written. Okay. So del phi upon del r would be minus alpha e to the power minus alpha. This is 1 upon r plus alpha upon 2. And then I will have to write some e to the power minus alpha r. And then I have 1 upon r plus alpha upon 2 will be 0. So I'll write minus 1 upon r square, and this is it. Okay, is that clear? So this will be my del phi upon del r. So del phi upon del r is nothing but it is minus alpha e to the power minus alpha r. So I have differentiated this and kept this as it is, and then I have kept this as it is and differentiated this. So overall, del phi upon del r would give me what? So del phi upon del r would give me minus q upon 4 pi epsilon naught. Let me first add up all these terms. So I'll just take r square common. So it will be 1 plus, I think this will be alpha r, and then this will be, I think, alpha square r square. Okay, so this is how it is. So what you will do, you'll simply take r square as a common. So r square, if you take common, you will come, this r square will come here. So this will be r. So this is plus alpha r, and then this is alpha. This is alpha square r square. So overall, you know what is your del phi upon del phi. Now, if I want to evaluate my del square phi, what it will be? It will be equals to 1 upon r square. This will be equals to del by del r of, and again r square. If you just take an multiply this r square, so it will be minus q upon 4 pi epsilon naught. Then you have e to the power minus alpha r, 1 plus alpha r plus alpha square r square upon 2. Okay. Now, if you differentiate this entire term, what you'll get? You'll get 1 upon r square. And then you have minus, you just take this minus q upon 4 pi epsilon naught outside. Okay. And then you have this minus alpha e to the power minus alpha r. And you have 1 plus alpha r plus alpha square r square upon 2. And then again, you keep this as a constant, e to the power minus alpha r. And then you have this, you take the derivative of this. This will be alpha. This will be alpha square r, if I'm not wrong. Okay. So overall, this will come as minus q upon 4 pi epsilon naught r square. Okay. And then you'll get minus alpha e to the power minus alpha r minus alpha square r e to the power minus alpha r, then minus alpha cube r square upon 2 e to the power minus alpha r, then plus e to the power minus alpha r, and then plus alpha square r e to the power minus alpha. This gets cancelled, this gets cancelled. Overall, this remains to be the case. And overall, I can express my entire thing, but also remember that all of these things that I'm doing is valid only for r not equal to 0. Because if I'll do another approach also, but right now, whatever approach I'm telling is only valid if I want to evaluate my expression for r not equal to 0. So basically what is happening is I'm evaluating all these things. That is my evaluation for this Laplacian of phi is only for r greater than 0. I'll suggest you another approach later on, but right now the first approach, that is a tricky kind of approach that I'm taking. I'm just assuming that my r should not be equal to 0, that is r is greater than 0. If my r is greater than 0, then whatever I'm writing right now is completely valid. There is no issue about it. There is no issue about it. So what will happen? What will happen is my entire thing will become, this entire thing will become what? Sorry. This entire thing will become del square phi will become what? Del square phi will become q alpha cube upon 8 pi epsilon naught. And this is, I think, e to the power minus of alpha. Okay. So it is like, and del square phi, it is the case that minus rho r on epsilon naught will be equals to del square phi. So rho as a function of r can be written as minus of q alpha cube divided by 8 pi, and then you have this e to the power minus alpha. So rho as a function of r is given by minus q alpha cube e to the power minus alpha upon 8 pi. Now, if you see the options, the options are not having 8 pi. So what you can think is probably while doing answer to this particular problem, they might have taken this in CGS unit. And in CGS unit, your 4 pi epsilon naught is 1. So overall, this 2 can be expected. Otherwise, I do not expect 2 here. But somehow the TIFR problem has given this as 2. So overall, when I evaluate, it will come as minus q alpha q upon 8 pi. So had I written this particular 8 pi epsilon naught as 1 here itself, then obviously I would have got 2. So don't worry about it. Overall, understand that there would be some minus q alpha cube, minus q alpha cube. And if you write this 8 pi epsilon naught and you write entirely this entire thing as 2. So overall, you can expect this particular answer to be a probable one. Obviously, the answers given to you are not it does not contain epsilon naught. So probably they might have taken this 4 pi epsilon naught as 1 in CGS units, and they may have done this particular problem. So don't worry about it. So overall, this particular thing may have what I want to suggest is, see, what I'm trying to tell is, let's say if your 8 pi epsilon naught was not there, so if 4 pi epsilon naught was not there, so if 4 pi epsilon naught was not there, then this would have yielded you minus q upon 2. Okay, and anyway, this epsilon naught would have been there. If you multiply it there and you absorb it in this constants, overall, you can say that most possible answer would be this. So what I want to say is, just write this. You just multiply epsilon naught and you just absorb this epsilon naught into this constant. And if you absorb this in this constant, what will happen? This will in CGS will become 2. So overall, this will be your charge density, which gives rise to the potential given above. And you have to understand that this is q alpha q. This you can take dash and ultimately write e to power. Okay, but this particular charge density is only valid if your r is not equal to 0. Only if your r is not equal to 0, and certainly r must be greater than 0 for this. So if your r is not equal to 0 and r is greater than 0, only then you can expect this kind of thing, because overall, if you see, if your r was 0, then this del square operation is not. I will also do this particular problem in a different fashion altogether, but right now understand this thing. Is that clear? So this is like minus q alpha q upon 2 e to power minus alpha. This is one thing that I have already done. Okay. Now, if you see the options, in all these options, there is some Dirac delta function associated. So how to get this particular Dirac delta function? So that I would do certain manipulation, and that manipulation would be see. Now I cannot go towards r equal to 0. So what I would do, I will just go towards 0. That is, I will approach as close as possible to 0. So if r tends to 0, then how is my potential? So my potential is q upon 4 pi epsilon naught, and then I have I think 1 plus some alpha r divided by r, if I'm not wrong. Let me see. Otherwise, there would be a mistake while doing it. Alpha upon, sorry. And then you have e to power minus alpha here. Okay. So overall, this is your expression for the potential. Now, if I write as r tends to 0, and if I linearly also expand my e to power minus alpha in this format, even if I take higher term also, this is a kind of expansion that I can have. Okay. And if I just, because since r tends to 0, so obviously r square will be way less than your r. So I can forget about all these higher order terms. And if I just retain these a few terms, then my phi as a function of r will be q upon 4 pi epsilon naught. And you just take r here, and then you have 1 plus alpha r upon 2. And then you have this 1 minus of alpha r. Okay. So overall, this particular expression, you can see phi as a function of r is q upon 4 pi epsilon naught r. And then you have this 1, and then you have minus alpha r. Then you have plus alpha r upon 2. And then you have minus alpha square r square upon 2. And there would be some higher order terms which I'm not interested in right now. Now, as r tends to 0, all these terms goes towards 0, and only remaining term is 1. And overall, as r tends to 0, whatever my potential remains is close to 1 q upon 4 pi epsilon naught r. So I can expect, I can see that as r tends to 0, my potential reduces to, so as r tends to 0, the potential given above, reduces to what? It reduces to potential of the point source. It reduces to potential of the point source. If it reduces to the potential of the point source, it implies what? It implies that there exist point charge at origin. You can see that there exists a point charge at origin. So basically, this is what? This is like having a point charge at origin and at a distance r, you are writing the potential as a function of r as kq upon r, where your k is 1 upon 4 pi epsilon. So you can expect, so you can write that this potential corresponds to potential due to point charge, and which implies that your q is at origin. And if q is at origin, then the volume charge density of such a point charge is written as q Dirac of r. So overall, my overall density can be written as q times Dirac of r minus q some alpha dash ka whole cube divided by 2. In this alpha dash, lately you again write some constant. So q times alpha dash ka whole cube e ki power minus alpha r. So overall, this particular thing, again you write some constant. So overall, I can write my charge density as q times Dirac of r minus q alpha over 2 and e ki power minus alpha. So this is your correct option. So the correct option to this particular question is, I think, C, and which indeed was given in the. So don't worry about all these things like alpha upon 2. However, you can see that in all these questions, this was the main thing that was differentiating. But I think such kind of things is generally TFR plays with your head also at times. So most probable answer that I see, it cannot be an answer for sure because you do not have a negative charge at the center. This cannot also be in, because see what is happening is, if you try to write this in 4 pi epsilon naught, then you only have this 8 pi epsilon naught here. So 8 pi epsilon naught is 2 times your 4 pi epsilon naught. So in any case, you can write this as 2 in CGS, or you can just multiply epsilon naught upon below and then try to write this in CGS. So overall, this happens to be the right answer. And this is what is my explanation. If you really find there is some error to it, kindly let me know.